dissolving it in water and testing it with a pH meter. And yet in a Lewis acid, Lewis base reaction, you can think of an alkene, say, as a proton donor under certain circumstances. Now, by the time you get to an alkyne, now you've got 50% S character in your CH bond. And now these are reasonably acidic. They're still very weak acids. Your pKa is only 25. That's really, really, really weak still. It's not even like water, which you think about as an acid forming hydroxide anion. It's still a very weak acid, or alcohol forming an acid, giving up a proton and forming an alkoxide anion. And yet our pKa is about 25. And I'll show you an implication of that in just a moment when we start to talk a little more about alkanes. But the point of this comes back to what I was saying before about about Grignard reagents being very reactive toward water. A Grignard reagent acts as a base with water. And so if you expose a Grignard reagent like butyl magnesium bromide to water, the water acts like a Bronsted acid, and you get butane and bromomagnesium hydroxide, a mixed salt here. So this is a Bronsted acid, Bronsted base reaction, if you think about it. We have water acting as an acid on the left half side of the equation. We have our alkane as an acid on the right side of the equation. And because the pKa difference is so humongous, the pK of water is 15.7, the pK of butane is about 50, I don't even bother to write an equilibrium arrow. The equilibrium constant is 10 to the 34th, right? It's 10 to the difference in pKa's. That reaction lies so far to the right that there's just no component to the left on it. And that's true with whether it's with water or an alcohol. And so just by comparison, imagine for a moment I wrote, let me pick a particular alcohol. We'll pick ethanol as an alcohol. And so now we would get butane and a ethoxy magnesium bromide. And of course, this would be the same with a carboxylic acid, or just about anything that you would normally think about as even mildly acidic. All right, well, Grignard reagents are one of a broader family of organometallic reagents. Another member of the family that reacts very, very similarly are organolithium reagents. And so if we wrote Grignard reagents sort of generically as RMGX, that would be a generic way of writing a Grignard reagent. We can write organolithium reagents generically as RLI. Organolithium reagents are formed by reacting alkyl or aryl halides. Again, we're talking iodide, bromide, chloride with lithium metal. If I write a balanced equation, say, for bromobenzene and lithium, it takes 2 lithiums. And that makes sense if you think about it, right? We're carrying out a 2-electron process here, and lithium has 1 electron. So magnesium has 2 electrons. And so a balanced equation becomes that we get phenyllithium plus lithium bromide. And again, organic chemists are awfully, awfully bad about writing products of reaction. So I'll put the lithium bromide in parentheses because I might not write it. So typically, if I were writing this as, say, a synthetic reaction, and I imagine generating an organolithium compound and, say, reacting it with an organic compound, I'll give you an example of what I might write. So I might take bromobenzene, or I might take chlorobenzene if I wanted, treat it with lithium metal. Now, organolithium reagents can be generated in ethers. An ether can serve to coordinate, but they also form clusters, and so they actually can be generated in other solvents, including hydrocarbons. I'm just going to skip the solvent here because it's much less important than in a Grignard reaction. And let's say as my partner, since I gave you a ketone before, I'll take an aldehyde. The aldehyde I've chosen is pivaldehyde, that's the trivial name, or 2,2-dimethylpropanal would be the IUPAC name. And again, I'll imagine doing some type of aqueous workup. I'll just write H3O plus here to indicate I haven't specified the acid. It could be aqueous HCl, it could be aqueous sulfuric acid. One that I personally like to use in my own laboratory is aqueous ammonium chloride, which is a very mild acid and very good for workups of reactions like this. Anyway, after our workup, the product now has a new carbon-carbon bond, like so. And of course, because we've generated a stereocenter in the molecule, we've generated it as a mixture of two enantiomers. We've generated two different enantiomers in equal amounts. We've generated the racemate. All right, in part because your textbook mentions various different organometallic reagents at this point, I want to follow along, and in part because I want to remind you of what I think are really useful items, and in part because I want to tie into this concept of pKa. I'd like to, at this point, talk about acetylide ions. And I see I have a question.
Yeah, you sort of erase the equation, but for the second equation, when magnesium bromide is attacking the ethanol, why doesn't the magnesium bromide bond to the OH but instead bond to the ethanol?
What's that? Oh, the question was, why doesn't the magnesium bond to the OH? It doesn't, well, there's no OH. Oh, you're saying in that reaction, because the ethanol has now given up its proton to react with the butyl part. So the proton has come off of the ethanol onto the carbon of the butane,